Hello and welcome to the Colorado Fruit and Vegetable Growers Association Lunch and Learn webinar, Getting Wise, new irrigation scheduling app from Colorado State University. I'm Adrian Card with Colorado State University Extension and board member of the Colorado Fruit and Vegetable Growers Association. I'll be your host for today's CFVGA Lunch and Learn webinar. This CFVGA Lunch and Learn webinar is part of the Irrigation Tech series intended to bring growers the best in technology and management practices for optimal irrigation. Today's webinar will explain key information and best practices in irrigation scheduling with the new Wise app from CSU. The Colorado Fruit and Vegetable Growers Association is the go-to resource for Colorado's fresh fruit and vegetable farmers. We connect Colorado growers with industry, government, academia, and consumers to strengthen and expand Colorado fresh fruit and vegetable production. For more information about CFVGA, go to coloradoproduce.org and follow CFVGA online at facebook.com/CFVGA. During the presentation, mouse over the bottom of the Zoom window to find a toolbar, and in that toolbar, you'll find a button for Q&A. Enter your questions there for our panelists. And today's webinar will be posted for CFVGA members viewing to coloradoproduce.org/water. Should say water instead of labor. Our presenter today is Alan Undalis, Associate Professor of Irrigation and Water Sciences at CSU. And Alan, before I pass over screen sharing, I want to say thank you so much for being with us today, and thank you for all your work in irrigation management in Colorado.
You're welcome.
So I'm going to pass screen sharing to you now.
All right, thank you, Adrian. So this is the presentation on the water irrigation scheduler for efficient application, and we just call it WISE for short. And this is an online tool that was recently developed here at Colorado State University with the support of the USDA, National Institute of Food and Agriculture. So let me start off by introducing the concept of depth of water, because this is really what the WISE tool is trying to achieve, is to estimate the depth of water, or the equivalent amount of water, typically given in inches, inside the root zone of a growing crop. So this depth of water, shown here as dW, is simply the product of soil water content by volume, and this can be given in inches of water per inch of soil. And that's what soil water content by volume means. And this can be measured, for example, using a soil moisture sensor that's installed into the root zone, or, as I will show you through the WISE presentation, a model that estimates this soil water content on a daily basis. So this soil water content is an inch of water per inch of soil. So you can see there that it is expressed per depth of soil. So you have to multiply it by the root zone, or however deep that soil, that root zone layer is. So once you multiply those two numbers, you get an equivalent depth of water, which is, again, in inches of water in this case. So here on the right side of the slide is just a representation, a hypothetical representation of the full root zone. Now, typically soils have around half of the volume of the soil occupied by solid parts of the soil, soil particles like sand, silt, and clay. Then the rest, the other half, is occupied by either air and water. And that depth of water is really just that variable that it can go up and down, occupying that other half of the volume depending on the water content. So this is how I like to simplify the concept of available water, because WISE tries to estimate the plant available water in the root zone. So available water is the water content of the soil between field capacity, FC, and permanent wilting point, or PWP. And we estimate this in WISE using data from the National Soil Survey database from NRCS. So they have a survey of all the soil types across the US, and they give this this range, or this difference between field capacity and permanent wilting point. So we call this the available water capacity of the soil. And the deficit, the D, is really our tool for managing irrigation in terms of the amount and also the timing of irrigation. So you can see here, the D is this red region of this bucket diagram. So this is just like a fuel gauge. So if this were all blue, then the soil is full up to field capacity, and there is no need for irrigation. But the D here is indicating that there is a deficit. So the deficit is just the amount of water that the actual soil water content is below field capacity. So that's called the deficit. And in irrigation management, it is more convenient to track this deficit on a daily or a weekly basis, because this indicates the net irrigation water requirement that is required to refill the root zone or the profile to field capacity. So the last thing I'd like to point out on this slide is the term MAD. So the MAD is called the management allowed depletion, or management allowed deficit. This is our threshold for irrigation, and this is typically set around half or midway between field capacity and wilting point. So that's why you see this red line here. That's the management allowed depletion. Depending on the crop that you are growing, this MAD can be closer or can be moved up to field capacity, meaning that this will be typically for crops that are more sensitive to water stress, and you don't want that deficit to grow too much. So in terms of depth of water, this DMAD, DMAD is what is representing the depth equivalent amount of water in inches that it will take to move from field capacity down to that MAD. So when we try to manage irrigation, what we do is we look at this deficit in the soil, compare it to the management allowed depletion, this DMAD. As long as the deficit is smaller, okay, does not go past the MAD, then we assume that the crop is fine and is not undergoing water stress. So that is the main concept behind deficit and available water. So if we say that the deficit is the net irrigation requirement, that is the amount of water that you would want to apply through your irrigation system. So for example, if you have a sprinkler system, you would want to set your system to apply this much, that D, with some consideration for any losses. So you might have to add a little bit more if you have losses from evaporation, and runoff, for example. But if you apply this much to the soil, then the deficit goes back to 0. So D is equal to 0 if the soil water content is at or above field capacity. So this next slide seems to be complicated, but it's actually fairly simple once you notice that what this is showing is just how we keep track of this deficit, which is that D, the current deficit in the soil profile. We keep track of this using this accounting equation or formula, very similar to how you would do a bank account. So all the additions of water are reducing the deficit, so they have minus signs. It's another way of thinking about it, since we're tracking the deficit, or the how much the soil water content is below field capacity. So the water additions actually reduce the deficit, so they actually have minus or negative signs. Precipitation is an input, so it reduces the deficit. Irrigation also reduces the deficit. And for fields that have a shallow water table, there is also a possibility where you can have capillary rise, which is the C here. But for most situations, this just is 0, because most fields don't have that problem of a shallow water table. So what adds to the deficit are represented in positive variables here. So the main variable that adds to the deficit or makes the deficit bigger is this ET, crop evapotranspiration. And this is really the biggest component of the daily water balance, this ET. And this is simply just evaporation from the soil and also from the leaves of the plant, and transpiration through the stomates, the pores on the leaves of the plant. And then the other possible losses are which add to the deficit is the surface runoff, SRO. That's just water running on the soil surface. And then the deep percolation, which is water draining from the root zone and not being able to be used by the crop. So that's how we do the water balance on a daily basis, and that's what WISE is trying to do. And mainly relying on weather stations, automatic weather stations across the state to estimate this P, the precip, and also the ET. And then the user has to input these irrigations, the actual amounts of irrigations. And we will run through a quick example on WISE, and this should be clearer. Okay, I just want to emphasize the concept of depth of water and deficit by using this example. So this is an example of a soil root zone that has layers. And this is what happens most of the time, is that your soil profile is not uniform, and there are soil layers or horizons that have different available water capacities. So this example here is showing a soil layer from 0 to 12, 12 to 24, and 24 to 36 inches. So each layer having 12 inches of thickness. And also shown is the field capacity, designated in terms of volumetric field capacity, which is inch of water per inch of soil. So 0.3, 0.29, and 0.4. Wilting point is also shown. And then you will need an estimate of the actual soil water content of the soil, also by volume, and it's given here in this example. So again, this could be from a soil moisture sensor, soil moisture sensors at these different depths, or we could be using a tool like Wise, which has that water balance model that tries to keep track of this water content. So for the example, I'm just going to show the top soil layer, which is the 0 to 12 inches, and just showing you how we get to a number for that soil water deficit. So first of all, the available water capacity, AWC, is simply the difference between field capacity and permanent wilting point. So if we take the values of FC and PWP, that's 0.3 minus 0.13. So that's 0.17 inches of water per inch of soil that's available to the plant. Okay. So once you have that available water capacity, you multiply it by the thickness of that soil layer, which is 12 inches. And what you get is the equivalent depth of water that's available to the plant, which is 2.04 inches. So that would be what would be available to the plant between field capacity and wilting point. Okay, but we said that we will not let the plant use all of this available water, but we will set a management allowed depletion. So the next step is to take that available water capacity of 2.04 inches and then multiply it by a management allowed depletion, which is a number, a decimal number, usually indicating the fraction of the available water that you will allow the plant to use before you irrigate. So as I said, for most crops, this is around 0.5 or half of the available water capacity. So 0.5 times 2.04 gives you 1.02 inch. So this is really the key number that we're after, is this management DMAD. And we just need to watch that our deficit for this layer does not go bigger than 1.02.
Alan, for our vegetable growers listening, we know that some of the management allowable depletions can be as small as 25% of available plant water.
Exactly, yep. Yeah, so for vegetables which are more sensitive to drought and water stress, yeah, this number, MAD, would be lower, just like Adrian quoted, 0.25, 0.3. Those are typical numbers for vegetables. So finally, the deficit is going back to the difference between field capacity and the actual soil water content. Okay, so 0.3 comes from this field capacity number here. The actual water content, soil water content in this example is 0.2. So you have to subtract that, multiplied by 12 inches, the thickness of the soil layer. And so our actual deficit for that first or that top layer is 1.2 inches. So that's how you get to a deficit number. And if you do it for the other remaining layers and add them up, we have a deficit of 3.72 inches of water in this whole profile of 0 to 36 inches. And our management allowed depletion is 3.18. So in fact, the deficit that we have here is already past or bigger than the management allowed depletion. So definitely this example is showing that you need to irrigate. In more visual view of that example, this is how it would look like, just using that bucket diagram. So you would have management allowed depletion here, available water capacity of 6.36 inches, and then our DMAD that we calculated for the profile was 3.18 inches, but our deficit was already 3.72 inches. So it went past this MAD, and so it definitely needs irrigation. So these notes on the side or just describing the status of the water in the profile. So currently, the soil profile has a deficit of 3.72 inches, which is already past the MAD. Of course, most irrigation systems, especially sprinkler and drip, cannot apply 3 inches, 3.7 inches all at once. So this is a guide, but you have to indicate in the Wise tool, indicate how much you apply relative to this deficit. But that's really how much you need to get back to field capacity. Okay, so as I mentioned, Wise uses weather data, and I'd like to emphasize that the choice of the weather station is very important. So if you have a field that is nearby a weather station that looks like this, which is well-watered grass surrounding the weather sensors, this is an ideal source of weather data. And if you have a weather station like this, which is surrounded by dry ground and it's really no irrigation going around the surroundings, that would tend to overestimate your evapotranspiration requirements. And this would not be a good source of weather data. So just really briefly, I'd just like to go through how we estimate the ET, the evapotranspiration. So we estimate the ET using what is called the crop coefficient. And this crop coefficient has to be developed for each specific crop that you want to schedule irrigations on. This is a photo of a lysimeter. It's an instrument that measures the amount of evapotranspiration and also the whole water balance in the soil profile. So this is just showing the surface, but underneath the ground, this is like a pot, a big pot of soil that is growing an active crop. So what we do is we get a reference ET, what we call ETR, reference ET, from the weather stations. We estimate that using the actual solar radiation, wind, temperature, and also humidity. Okay, so that's the potential amount of ET that's possible given the weather conditions. Then we try to measure the actual ET of the crop, and typically we do this using a lysimeter that can accurately measure that evapotranspiration. And once you have these two numbers, you get the ratio between the actual crop ET and the reference ET, and what you get is the crop coefficient. So this crop coefficient is then multiplied every day. We calculate the reference ET from the weather station. And as the crop is growing, this KC also changes and typically increases as the crop grows. These are just some pictures of the actual mechanism of the lysimeter. I just wanted to show it because it's pretty interesting how it's a big structure and it's very precise. Yeah, it can measure close to a hundredth of a millimeter of water. So that's why we can get a very precise reading of ET. This is how the lysimeter looks like with corn growing on it. And this is an example of a crop coefficient that was derived from the lysimeter data. So this is showing the x-axis in days after planting. And you can see that the crop coefficient starts really small because there are still only seedlings and it's mostly soil evaporation. But once the seedling emerges, then you have rapid vegetative growth and that crop coefficient just increases rapidly. And then it tapers off once the canopy is done growing, adding leaves. And then it starts senescing some of the leaves starts dying off towards the end of the growing season. So you have this drop off in the crop coefficient. So that is how we model or estimate the crop water use or evapotranspiration. Now, previously, and we still have this, across the state of Colorado, we have a network called the Colorado Agricultural Meteorological Network, or COAGMET for short. And this is just showing a map of all the weather stations that we have. Well, this network already gives an estimate of the precipitation and also the ET. And this screen here is showing you an example output from COAGMET. So you could have the daily values of different crops that you select from the menu. And then it also gives a reference ET, the potential ET from the weather conditions each day, and then also the precip. But it does not account for the actual water content in the soil. And so this approach would not account for any shortages in water stress in the soil. And that is what WISE is trying to do, is in addition to estimating ET, we are trying to estimate the actual water content in the soil, which is the basis for irrigation. So here is a diagram of the WISE system, and just taking a minute here, it's simply taking the WISE system is simply taking the weather network, and right now we have COAGMET, which has about 65 weather stations across the state, and we also added about 20 northern water stations, this NCWCD, right here at the lower right. So those are the two main sources of weather data. Then we have what is called ERAMS, this Environmental Risk Assessment and Management System, which is a platform, and it's a GIS, or a Geographic Information System, that is freely available and accessible on the web. So we take this weather data, run it through ERAMS, and ERAMS also has access to the NRCS Soil Service Geographic Database, which is our source of available water capacity for the root zone. Okay, and right here are just a bunch of cloud services. There's really no concern about the details about this, but we do use a cloud server to process all this data, and we have virtual machines so that every single user who logs into ERAMS actually has like a mini computer or a virtual machine that will run the model, run the water balance model for their individual farm or field. So the client or the interface is a web client, which is any web browser that you have on your computer. And we also have mobile apps that I will show you some images of in a minute. Okay, so these are just some screenshots of WISE. So again, that's what WISE stands for. This is the ERAMS interface using Google Maps, and then this is the WISE control panel where you can look at your farm parameters and also your irrigation schedule. And I will show a live demo of this. What you get is a time series, or just a graph of the date as the growing season progresses. And the blue line here shows the up and down movement of that plant available water in the soil. And that red line that you see is that MAD, or that management allowed depletion. The green line is the field capacity. So the way you would use Wise is you would just look at the curve, that blue line, and just make sure that that blue line stays in between that or above this MAD and close to or below the field capacity. We have tested Wise for several crops, mainly corn and sugar beets. So let me just show you an example output for sugar beets. A graduate student went out every week and tracked the actual water content in the soil. In a sugar beet field, we put sensors in there and also used the nearest weather station to the field to estimate the water balance. So this is an example from a sugar beet field near Gilcrest in 2013. And you can see the gross irrigations, the irrigation amounts applied through a sprinkler system is given here in squares, orange squares. There's rainfall that happened throughout the growing season. Those are in green circles. And then this is showing the deficit. The blue line is showing the deficit that goes up and down depending on whether there is irrigations, rainfall, and of course, what is making this deficit grow is the ET, the evapotranspiration. Okay, and again, the red line is indicating the management allowed depletion. So you can see here that the farmer actually did a good job of maintaining that deficit, not to go past the management allowed depletion. Only late in the season here was an occurrence, but that was already the end of the irrigation season, so that did not actually matter. And I just want to point out that we compared the Wise deficit to the observed deficits from the soil moisture sensors. And Wise did a pretty good job of coming close to those observed deficits, except for a date, for example, here, it's kind of off in time. But most of the time, Wise did a good job of estimating the observed soil deficit. So as I mentioned, we have a smartphone app that synchronizes information with the Wise web-based tool, and we do have it for the iPhone and also Android platforms. So this is just some screenshots of the smartphone app. So you have to log in. Every user of Wise needs to create their own account, user account. So once you log in, then it comes up with a list of projects or fields that you are managing for irrigation. So once you see your fields or projects, you can select a specific field. And what it gives you is a summary. And again, it uses just a simple fuel gauge analogy where you have, or a bucket analogy, where you see the deficit in red, and the deficit is also written on the right-hand side. So in this example, the deficit is 1.35 inches. So just by quickly going through the app, you can know exactly how much water you need to apply. So in this case, 1.35 inches. If you click the I, it gives some information, some definitions of the symbols that are used on the app. And if you click on Add Irrigation, you can synchronize whatever. If you are at your control panel, for example, if you have a pivot or a linear move sprinkler system, and you type in 0.49 inches of water, for example, that you're applying, you can type it into the app and then click Update make sure that you have the right date, and the app will send this to the server, the Wise web server, and it will update or recompute the soil water balance for you. We also have a simple calculator for estimating inches of water based on flow, like cubic feet per second or gallons per minute. If you have a flow meter on your irrigation system, and you also know the runtime and the total acreage that you're irrigating, you can use this simple calculator to estimate the equivalent inch. And this app can send that final calculated inches of water to the web server as well. And the last feature is you can look at yesterday's weather. So currently we do not have real-time access to the weather data. We can only go back as far as yesterday's weather, but hopefully we can improve on that. But that's the app. And for further information on Wise, I would like you to visit Wise.colostate.edu. And that is the main source of information for this tool, is that website. Just like to acknowledge the whole Wise project team. This took a huge effort over 4 years to develop this. And we did have significant funding from USDA, as well as these other sponsors of field as well as programming efforts that were done for the tool. Okay, so we are ready to go into the live demo. So I will open up my web browser, and in terms of selecting a web browser, we have found that Firefox works really well with Wise. So if you are having problems with Internet Explorer or Chrome, you might also would like to try Firefox using Wise. So this is the main website, Wise.colostate.edu, and we have useful information, background for a new user. We have a tutorial. If you go and scroll down and click on Get Started, we have some videos that show how to get a user account, and also gives an example of setting up a field for irrigation scheduling. So that's a useful resource. Now, the main tool is on the eRAMS platform. So if I click on the eRAMS platform link here, then it takes me to the eRAMS login page. Okay, so for someone to use Wise, that person would have to create an account, and it's fairly simple. You can just sign up. There's a link here to sign up, and it's fairly straightforward. So I am going to log in. I do have my own account, so A. Andales, type in the username, and then the password you type in. And once you type in the password, you get this projects view. So on the left-hand side, you have to click on projects to see a list of all the projects that you have. And I have a bunch of projects because I have used Wise in tracking or irrigation scheduling for different fields. So that's why I have so many projects. Okay, so what I'll do is I will create a new project and just run through an example. So I click on the plus sign here, create project. And the next thing it asks is, it asks for a project name. So you can give any name And I will just call this, I will use a dry bean crop as an example. Dry bean example 2016. Okay, so that's my name of the project. And then for the project type, make sure that you drop down and select irrigation scheduler. Okay, there are other tools on ERAMs, and that's why you have a drop-down list of other tools. But make sure you click on irrigation scheduler. And if you are starting off with a new project, you really don't need to do anything for this layers. Okay, so that's all you need. Click OK. And what it does is it adds that new project in your list. Okay, so now I see that project, Dry Bean Example 2 2016. So I click on it, and it will open up the main Wise interface. On the right-hand side is the ERAM's geographic information system. So it's pretty much using Google Maps as the base layer. And then here is the control panel for all the functions of Wise. Okay, so the first thing that you have to do is draw your field. So that's how we get the soil properties of your specific field, and we also locate the nearest weather stations. If you know your GPS coordinates for your field, you can type it into this Zoom 2 window on the map. So I'm gonna type in a GPS coordinate here, 40.22926, and I just randomly selected this from a field that we could use near Longmont. So that's the latitude is 40.22926, and for the longitude, don't forget to type in the minus sign because we are to the west of the prime meridian. So minus 105.07377. Okay, so that's the GPS coordinates that I typed in, and if I click enter, yeah, it zooms in immediately to that field. Okay, so I will kind of zoom out because I just randomly selected this pivot here, and I would like to use this as an example. Okay, so now once you zoom into your specific field, you have to draw the field boundary. So you use the draw tool on the control panel here on the left-hand side. Since this is a pivot or a circle, I will click on the draw circle tool, go back to my map, and start from the center of that field and hold my mouse and drag out. So this is a really convenient feature of the GIS. So once I've drawn the perimeter of that field, I release my mouse and it'll ask for a field name. So let's just call this a dry bean field. Dry bean field. Click OK. So you can use any name that you want. So what Wise does is it tries to extract the available water capacities of the soil inside that field. So it is trying to get soil layer information from the state geographic database. So we'll let that finish up. But as you can see, Wise already identifies on the left-hand side the nearest weather stations, and it has located 2 northern water stations that it can use for estimating precipitation and also evapotranspiration. Yeah, and you will notice that as you hover over the name of the weather station, there is a power button. So you can turn each weather station on or off. Yeah, but for now, I will use these two weather stations, because the advantage of using two weather stations, if one of them goes down, Wise can still have weather data to use for the water balance. Okay, so that's our field. And if you click on the control panel on the shovel icon, that will show you the soil types, the major soil types in the field. And what Wise does by default is to select the soil type that occupies the biggest area in the field, which is this Colby silty clay loam in this example. And it will use the soil properties, the available water capacity of that soil type in the irrigation schedule. So you have the option of selecting any other soil type to schedule irrigation. But for now, that's the limitation of Wise, is that it can only use one soil type to represent the whole field. Okay, so the next step is to click on this gear icon where you can select your crop. So since I call this the dry bean field, the crop type, you can drop down, and so far we have these crops available. And so if we were to add vegetables, other vegetable crops, for example, we would need to develop crop coefficients for those vegetable crops and then put them or add them into Wise. So since I don't have vegetables right now in the Wise tool, what I'll do is I'll just use dry beans. Okay. What you have to do is you have to tell it the planting date, and we will assume that we are working in 2016. Let's just say that we plant dry beans in June, the first of June, so June 1. We also ask for an emergence date, which is when the seedling emerges from the ground, because this is when we start estimating ET. Yeah, Wise starts estimating evapotranspiration on this date, the emergence date. So if you don't have an exact date, you can just estimate. But let's say in a week, the seedling emerges, so June 8th. And you can leave the estimated harvest date blank. The next step is just to input some irrigation information. So this is a center pivot that I'm using as an example. And it has spray heads without end guns, for example. And this is a really important number, is the efficiency of the irrigation system. So this is a number representing in percent how much the system actually gets water in the soil. So if it's set to 80%, that means that 80% actually goes into the root zone. 20% is lost by evaporation or spray drift and runoff. So you can slide this up and down, this efficiency number. And for this example, I'll just keep it at 85% efficiency. And you can scroll down, and you can also see the available water capacities. There's 3 layers in that root zone. Okay, so once you have everything selected, you click on Update. So make sure you click Update to save that information, and then click Done. And now the tool is set up for irrigation scheduling. So the irrigation schedule is accessed through this calendar icon. So this is supposed to look like a calendar. If I click, it calculates the water balance. So This is a tool that uses weather data, live weather data up to yesterday. So if you look at the summary that it gives, it went all the way from from June 1 when we planted, all the way to yesterday or today, August 23, 2016. And then it gives a summary of the water status. And you can see that the deficit is really big, way past MAD, and that is because we applied zero irrigations. Yeah, so this will run up to up to yesterday's date, and since we're almost to the end of the growing season, yeah, it just ran until yesterday's date. So there had been 1.3 inches of precip from June 1 to today, and then 5.63 inches of ET. Okay, so the way you would use this as a tactical tool is you would be looking at this deficit and making sure that that red bar does not go past the MAD. And so if we were just starting off in the growing season, okay, I'm pulling up the graph that the Wise tool comes up with. So you can see that because we have not added any irrigations, it's way past the MAD. There's two options of looking at the graph. One is called plant available water. So that's the number of inches of water available in the root zone. But what I like to look at is the water deficit, because the water deficit shows you the deficit every day, and the deficit is the net irrigation requirement that is required. So it directly tells me how much water I need to apply. Okay, so you can see that because we did not apply any irrigations yet, that deficit just grew and grew throughout the growing season. So let me add an example irrigation. So the way you use Wise is you just watch this blue curve and make sure that once it approaches the MAD, that red line, you irrigate. You should irrigate. So let's see, around June 8th, the deficit was 0.4 inch. So I will go to the table. So the table view is a spreadsheet. It goes on a daily basis and shows you the rainfall, the crop water use, and the key thing for a user is to input the correct gross irrigation amount. So this is the amount that you typically type in to your control panel if you have a sprinkler system, for example. So June 8th, let's say if you double click on June 8th under gross irrigation, you can edit, you can input an amount. Let's say I will irrigate or apply 0.4 inch, the same as the deficit that was indicated. So I click enter. The next thing is this is a web app, so you have to always click update. So update, and what it's doing is it's recalculating the water balance again. Okay, so you can see that on June 8th we applied 0.4, but because we set the efficiency of the irrigation system to 0.85 or 85%, you can see that under the effective water column, there is only 0.35 inches effectively going into the root zone. So that's what the efficiency does, is it estimates the effective water. Okay, so if we go back to the graph, that irrigation should show up. So you can see it's still a small, just a really small bar that shows up. You see irrigation right there, that bar. You see that the deficit goes to almost zero again because of the irrigation. So you just have to do this as you go through the growing season, you have to just watch that deficit. If it approaches the MAD, okay, again, let's see, on June 12th, it's starting to approach, yeah, the deficit again is 0.4. I'm going to go back and apply another irrigation. Let's see here, let's take June 14. Let me apply 0.54 inches because that's the deficit on June 14. Click update. So again, it's recalculating the water balance. And then again, you can go back to the graph and you can see that the irrigation we applied shows up, and it brings the deficit close to zero again. So that is the gist of Wise. It's fairly simple to set up. And once you have your field configured and your planting and emergence date and the crop type selected, then you really just have to watch this on a daily basis and make sure that that deficit does not go past the MAD. And we also have the app that can synchronize and also show this water bucket diagram and also show you the deficit. Okay, Adrian, I think that is the presentation on Wise. I'll turn it over to you.
Excellent. Thank you, Alan. Got a couple of questions here for you.
Sure.
You want to pass screen sharing back to me?
Okay, I'll stop share.
Perfect. All right, here we go. Questions. How many miles do I need to be to a station to have accurate weather data?
That's a really good question. And what I've been recommending to farmers, and this is based off of a study of weather networks on the Eastern Plains, but no more than 10 miles is what I would recommend. Because as you go past 10 miles away from your field, then you really are not getting a good representation of rainfall. So the highest variability in weather comes from that rainfall amount, precipitation amount. So in fact, if you could find a weather station that is within 5 miles, that would be the best.
Okay, great. Another question, how do I get management allowable depletions for vegetable crops?
Yeah, so we have several references. There has been a lot of research already done in the past for MAD for different crops. So the Food and Agriculture Organization has a publication called Crop Water Requirements. So if anyone is interested, I can also point the reference to that. That is available online.
Okay.
On the web.
Okay. Great. And one here, how do I determine inches applied for drip irrigation?
Yeah, so for drip irrigation, to have an exact number of inches, you would need to have a flow meter. That is key. So if you have a flow meter, then all you need, in addition to the flow, the water flow, typically in gallons per minute, is to have the area that you are irrigating. So that would be total number of acres. And then if you have the flow rate, the area, and then finally the time, how long do you run that drip irrigation system? Is it 1 hour, 2 hours, or 3 hours? So once you have those three, you can calculate the depth, the inches of water.
Okay.
Because the flow rate multiplied by the time gives you the volume of water.
Mm-hmm.
So the volume would be total number of gallons or cubic feet. You have to do some conversions.
Right.
So once you have the volume, you divide that by the area that is irrigated, and that gives you the depth.
Gotcha. Gotcha. Okay. ERAMS looks tricky to use. Are there tutorials, or can you assist me? Are there user guides?
Yeah. So on the Wise website, Wise.colostate.edu, we have a getting started link, and we have some YouTube videos that show you or demonstrate how to create an account and also how to go step by step in the ERAMS platform to create that field and actually get an irrigation schedule started. Yeah, so I would recommend any new user of Wise to look at those resources.
Okay. Okay. Here's one. How do I determine irrigation efficiency?
Yes, and that is kind of a tough number to get at, because you really have to know your irrigation system to get at a good estimate of efficiency. So the way we do it to get accurate numbers of efficiency is we take a soil water content sample of the soil profile before irrigation, turn on the irrigation system, and make sure that we know exactly how much we're putting through that irrigation system, turn it off, and then we take a measurement maybe 1 day later, take a measurement of the soil water content in that profile again. So the difference between how the water that was added into the soil from the before and after readings gives you an idea of how much actually went into the soil. Yeah, the difference between that and what was applied is what was lost, the water that was lost.
In the absence of doing a full calculation like that, sort of a field-based calculation, are there tables growers could use just to estimate?
Yeah, I would start with just some tables of typical application efficiencies for different irrigation systems.
Okay.
And there is a good publication from the Water Institute, the Colorado Water Institute, that has a table of typical irrigation efficiencies for different irrigation systems. Yeah, and that's also on, I believe it's online as well, and I can give the link to that.
Okay. Okay. And finally, someone is asking, and I think this was a somewhat of a request in your presentation, but how can I assist in developing crop coefficients for vegetable crops in Colorado? I think that's something that you need still, Alan, to build out this tool.
Yes, yeah, that's a great question. So I did show how we do it scientifically using a lysimeter, right? But the lysimeter is very expensive. It's very expensive to build a lysimeter. So the next best thing is if we can get a field that is actually growing that vegetable or that fruit crop, and we install sensors that can track the soil water content in the field. So then we can start with the just published values of crop coefficients. The Food and Agriculture Organization also has a lot of crop coefficients that are published for different vegetables and other crops. So we can start with that, and then we can calibrate Wise. We can calibrate by looking at what Wise predicts as a deficit, and then comparing that predicted deficit with observed deficits from the field.
Okay.
Yeah. So if we see that Wise is not matching the observed deficits, we can go into Wise and make changes to the crop coefficient.
Okay.
Yeah.
Would growers come? I'm sorry.
Yeah, and it's more of a curve fitting exercise.
Okay, gotcha. Well, growers would contact you if they wanted to participate in helping develop those crop coefficients for Colorado.
Sure, yeah, yeah. And as I mentioned, Western Sugar did support the WISE effort, and that was an output of that support that they provided. Was
Okay,
we came up with a crop coefficient for sugar beets for Northeast Colorado.
great, great. Okay, wonderful. Well, thank you, Alan, so much for this detailed presentation on not only soil water management, all of those components that going into understanding the background and also how to use WISE. I think that's a very good tool for decision making for irrigation scheduling, and really appreciate all your efforts, and hope growers will reach out to you and help build this tool so we can really start to use it for vegetable crops and tree fruit crops in Colorado. The recording will be made available to CFEGA members from the coloradoproduce.org/water website. Log in as a member for access there. And Alan, really appreciate all your time today. Great presentation.
I appreciate the time that you gave for me to present WISE. Thank you.
Thank you. Thank you so much.